I'm here with Lucas Liu, manager of our applications engineering team based in Ottawa, Canada. Today, we'll review the fundamentals of good engineering design as it relates to layout of GaN device power circuits. Enjoy the webinar. Thank you.
Thanks, Paul, and thank you all for joining this webinar. As Paul mentioned, my name is Lucas Liu. I'm the Global Applications Engineering Manager with GaN Systems. Today, we will be discussing the simple layout steps to maximize GaN design performance. GaN Systems is a gallium nitride power semiconductor company. We focus on the GaN or silicon technology for the power conversion market. We have 100 volts and 650 volts industry best performance enhancement mode GaN devices. We have been shipping parts to over 2,000 customers since the year of 2014. Our headquarters and research and design are in Ottawa, and the operations are in Taiwan. We have sales and applications engineers in Europe, Asia, and Americas. GaN is growing across many markets like consumer, industrial, data centers, automotive, energy storage systems, wireless charging, and so on. You can see many companies have demonstrated success with GaN systems component. The value of GaN will be totally different for different applications. For example, for the adapters, a higher system power density is enabled by the high switching frequency of GaN. The designers are able to reduce the magnetic size to achieve a much higher power density compared with a silicon-based system. On the other hand, like energy storage systems, the value of GaN is to maximize the system efficiency to reduce the cost and the size of the battery. In this case, the switching frequency will not be much higher than a silicon-based system, but the benefits using GaN will be significant as well. Despite the design priorities among efficiency, power density, and cost for different systems, it is clear that we want to use GaN to maximize the system net value and make the design easier, not the other way around. Let's look at a power electronics system. This is a GaN Systems 3 kW 2-pole PFC reference design. In the picture, you can see a fan, power stage, bus caps, auxiliary power supply, boost inductor, and so on. By the way, the EMI is fully passed in this design. So just like a silicon-based system, a GaN-based one will not be more exotic. The really unique and special part for GaN-based system is the power stage. Here we mean the GaN hub bridge and its driver board. It will only contribute 10 to 20% of the system cost and size, but 50% of the system loss and 100% of the DIDT and DVT noise. It will determine the magnetics design, the thermal design, and the EMI filter design. This presentation will focus on the design of the power stage in the backbone of the power electronics system. If we just replace a silicon device with GaN, due to the much lower figure merit and also the zero reverse recovery of GaN, the switching loss will be much lower. So the efficiency will be greatly improved. So the high efficiency will help to reduce the heat sink size, and also because of the smaller packaging of GaN. So there will also be some power density advantage if we replace silicon with GaN. The lower switching loss make it possible to increase the switching frequency with GaN. So if we do that, the passive component size will be greatly reduced. For example, like the inductor, transformer, and the EMF filters. So the advantage in power density will be significant. Also, a higher switching frequency make it possible to reduce the terms of the windings of the magnetic components, or with the same terms, we can reduce the delta B in the magnetic core. So it is possible to increase the efficiency as well. There are many great topologies and control algorithms are only possible with GaN. For example, like the two-tempo bridgeless PFC. So without GaN devices, the reverse recovery of the silicon MOSFET will just kill the system. So in such cases, the advantage using GaN will be huge. The device advantages together with the topology advantages. So the payoffs at the system level will be great. We can draw the conclusion that the GaN advantages mostly comes from the fast switching transition. So in order to fully utilize the performance of GaN, we have to be able to deal with the fast switching transition. The good news is it is actually quite easy to deal with them. There are only a few simple steps to follow. Over the past decade, the industry and academia has thoroughly studied the effect of circuit parasitics on switching transition. A lot of good papers have been published on figuring out what happened during the switching transition, how to model the switching waveforms, what's the role of each parasitic inductance, and how to extract parasitic inductance of circuit using simulation or measurement, and how to minimize the strain inductance in layout. GaN Systems also reviewed many customer designs and did many experiments to validate the proper design. So this presentation will only focus on the two master nodes for most system designers. Number one, which inductance matters. Number two, how to minimize the critical inductance. How is the DIT? DIT on L1 is very low, so let's use only shows any problem in the current. So let's get state 1, then we can get H2 turned off, so the in this current L1 high DIT will cap high side H2 output inductor L1 to the low side switch. So that will be some DIT. Because voltage is equal to L DIT. So DIT will induce unexpected voltage in the circuit due to the parasitic inductance. Here, the DIT is determined by the switching transition of S2. So with a fast switching transition, minimized parasitic inductance design is really important. We have 3 sections to go today. First, the effect of circuit parasitic inductance. And secondly, the simple layout steps to maximize GaN performance. And in the end, there will be a brief introduction to the available GaN systems reference designs. Let's look at the first topic. This is a list of the parasitic inductance in a power stage. To give a structure to this section, let's look at the conclusions first. Generally speaking, the inductance can be divided into three categories: the power loop inductance, the gate loop inductance, and the mutual inductance between the power loop and the gate loop. We usually call it common source inductance. The simplest way to describe the effect of the parasitics is that all of the parasitics will excite or participate in the VGS or VDS oscillation. So the design rule can be really simple, just to minimize all the listed inductance. It is a simple rule, right? However, in practical, it is very difficult to be implemented. The reason is, in system design, we have to do the trade-offs all the time. In order to know how to do trade-offs, we have to understand the priorities of each inductance. So here is a priority list we summarized. As you can see in this slide, the common source inductance is of the highest priority. Then is the power commutation loop inductance. Then is the gate loop inductance. This list might be different from what you heard about GaN. Seeing is believing. Let's look at the data. In order to verify the effect of parasitic inductance on the switching performance, we propose this DOE, the design of experiments. So the control group comes from the GaN systems reference design. We think the layout is optimal. As you can see in the table, the common source inductance, the power commutation loop inductance, and the gate loop inductance are all minimized. The design 1, 2, 3 comes from the most common first-time designer mistakes. So for example, like no Kelvin connection, or a very large gate loop or power commutation loop. But we did not put, in practical bad design. So all these designs are still pretty okay design. Just not optimal. So let's look what happened. The double pulse test setup will be employed to verify the switching performance of the power stage. The test setup is on the figure left. An inductor will be in parallel with a high side device, which is normally off, and the two pulses will be applied to the low side device. By doing this, any high power conditions can be emulated by this circuit. Because no heat is really generated, so the maximum switching current will not be limited, like continuous test. This is also a safer test. Usually hot failures will not happen. Please look at the waveform on the right. So during one double pulse test, one zero current switching on, one hot switching on, and two hot switching offs will be performed on the low side DOT. Let's look at the control group, GaN system half-bridge reference design. The power commutation loops, the gate drive loops, and also their mutual inductance are all minimized. Don't worry, the detailed design rules will be introduced in the next section. Let's look at the Maxwell quick 3D simulation result of the control group. Due to the magnetic flux cancellation design between the top layer and the second layer of the power commutation loop, the loop inductance is only 1.9 nanohenry. Please note that in order to measure the device current in this design, we insert a Rogowski coil into the power loop. So in practical design, the power loop inductance can be reduced to about 1 nanohenry. Also for the gate loop, all the components are placed as close as possible. and also a flash cancellation design is applied. So the total loop inductance is about 4.1 nanohenry. And Kelvin connection is applied, and also as you can see in this picture, the coupling between the power loop and the gate loop are minimized. So the common source inductance is really low. It's only 0.006 nanohenry. Let's look at the hot switching waveforms of the control group. As you can see in the picture, no undershoot and overshoot on VGS and VDS out of device SOA were observed. So reliable and efficient hot switching transition has been realized at rated current. A good EMC performance can be expected. As you can see, the voltage spike is only 88 volts at the maximum device current. Okay, time to look at the effect of parasitic inductance. The common source inductance, in other words, the mutual inductance between the power loop and the gate loop, is over the top priority. So as you can see in the schematic and in the equation, the common source inductance will feed back the DIDT in the power loop into the gate loop, so which can cause some parasitic switching, undamped oscillation, or even device hot failure. This is a non-optimal design with about 2 nanohenry common source inductance. Instead of using a Kelvin connection, in this design, a big source polygon are employed to connecting everything. I mean the power source, the drivers, everything together. So as you can see in the picture, the highlighted inductance is shared by both the power loop and the gate loop. So this is a common source inductance. So in order to figure out the effect of the parasitics, I mean the common source inductance, we keep the rest the same. So the power commutation loop is exactly the same as the control group. So this is the prototype. See, this is still a pretty compact design. So this is not a unrealistically bad design. Let's look at the waveform, see how it looks like. So this is a switching waveform with some common source inductance. As you can see in the picture, some fault triggering occurs at 10 amps, 400 volts. So this will cause some additional loss, EMI noise, or even device hot failure during continuous operation. So this is the effect of the common source inductance. And the solution can be really straightforward. If you look at the schematics and the layout, just use the Kelvin connection to bypass the common source inductance, as you can see in the picture on the right-hand side. So with the Kelvin connection, a predictable and efficient switching transition has been realized at full current. So here is our layout recommendation. If the device you choose has a source sense pin, please drive the device with them. Do not short the source sense pin and the power source pin together. For the device without source sense pins, please create a Kelvin connection in layout, as we did in the previous page. Of the second priority is the power commutation loop inductance highlighted in the picture. The power commutation loop consists of 3 components: the high side and low side switches and the decoupling cap. Power loop inductance will increase the undershoot and overshoot of the VDS during the switching transition, which could cause some EMI issues. On the other hand, the magnetic flux generated by the DIDT in the power loop can affect the gate loop or other components. So in order to verify the effect of the power commutation loop inductance, we took the control group board and removed the decoupling cap. Instead, we put a film cap as close as possible to the devices. So the flux cancellation between the top layer and the mid layer one were disabled. So the total loop inductance will be about 17.5 nanohenry. So this is not a terrible design. I mean, there's just no flux cancellation. So here are the test results on the 30 amps. 30 amps is a very typical number for this device running continuously in the system. And as you can see in the picture, the VDS overshoot during switching off has been increased to 550 volts. Please note that for a 650 volts GaN systems device, the maximum transient voltage is 750 volts. So there's still sufficient margin for a worse design. However, the EMI will suffer. On the other hand, we don't want the power loop affect the gate loop and the other components. So please still try to minimize the power commutation loop by a flux cancellation design. Okay, time to talk about the gate loop. The gate loop inductance might be the most famous inductance you heard about GaN. There are also some monolithic solutions integrating the drivers and GaN devices together on one chip. In these cases, the loop inductance, the gate loop inductance will be minimized. And so what's the difference? Let's look at the effect of the gate loop inductance. Here is the definition of the gate loop. And for the turn on and turn off process, the gate loops are different. So don't forget about the driving capacitor. Actually, it is the driving capacitor charging or discharging and the CISS of the device during the switching on and the switching off transition. The gate loop inductance will increase the VGS overshoot or undershoot and during the switching transition. Also, the mutual inductance between the gate loop and the power loop is really critical. As we mentioned earlier, this is the common source inductance of the highest priority. So here is a non-optimum design with about 14.1 nanohenry gate loop inductance. As you can see in the picture, this is not a very good design. In practical, the gate loops could be laid out much smaller. So again, we make all the other conditions exactly the same as the control group, so we can see the effect of the gate drive loop inductance. Let's look at the test result. So here is the hard switching on and the hard switching off waveforms of the non-optimum gate loop design on the rated current. As you can see in the picture, the only issue is the minus 4 volts on the shoot on the gate. But this is still within the device's OA. For GaN system devices, the maximum VGS voltage is from minus 20 volts to 10 volts. So due to the robust gates of the GaN system devices, the gate loop self-inductance is not concerned. It is clear that the design priorities is highly related to the device characteristics. For example, if the maximum negative VGS voltage for GaN is only 5 volts like most of the silicon carbide MOSFET, then the gate loop inductance is really important. But for GaN systems, GaN devices, if you heard that even 1 nanohenry inductance on the gate can cause a bad problem, that's not true. So in practical, we still suggest to minimize the gate loop to reduce the mutual inductance between the power loop and the gate loop. But the point of this slide is just don't overestimate the difficulty laying out a GaN-based half bridge. Let's look at the summary for the first section. So in this section, we reviewed the most common first-time mistakes and verified the effect of parasitic inductance by doing some experiments. The most important design considerations for GaN is to reduce the common source inductance. There will be some fault tolerance when you design the power loop and the gate loop, as long as you can make the return inductance as small as possible. But minimizing the parasitic inductance can make the system design much easier and also improve the system overall performance. For example, like system robustness, EMI, and efficiency. The next section is about how to do the layouts. According to the design rules we learned, we summarized 4 steps to do the layout. Step 1. Prepare the schematics and identify the components for each critical loop. We listed different gate driver circuits for different applications. This page shows a typical isolated gate driver circuit for single GaN device. In the table, we listed the priority and components for each critical loop. For example, for the power commutation loop, there will be 3 components, Q1, Q2, and the C bus. Please note that the other components, like the isolated power supply for the gate driver circuit and also the pull-down resistor, are not in any of the critical loop. So in design, if we don't have space, we don't have to put these components as close as possible. This page shows a half-bridge bootstrap gate driver circuit. It is exactly the same as the gate driver circuit for silicon MOSFETs. So in the table, we also list the priority and the components for each critical loop. So the ether driver circuit is very similar to the bootstrap half-bridge driver circuit. And the point of this circuit is to utilize the integrated driver of an analog controller, so that we can drive the device with a controller without an external driver circuit. So this is for low power applications. There is also a table here to set the priority and help identify the key components of each loop. As the first step of layout, let's make sure that we pay attention to the right components. The second step is to place the components according to the design priorities and the current direction. Put the components on the PCB board as close to each other as possible. And according to the current flow direction, set the components in sequence. If there is a conflict for minimizing all the loops, please refer to the priorities presented in the step 1. Here is an example of using an isolated gate driver circuit to drive the topside cooling device. So first, let's put the components of the power commutation loop into the system, which is of the highest priority. There are 3 components from the power commutation loop: the decoupling cap, and the high side and the low side GaN devices. So here, as you can see in the picture, let's put the 3 components in a row. And this is the most effective way to minimize the power loop. Also, in the picture, you can see the side view, because this is a topside cooling device. So the decoupling cap and the GaN devices has to be on the different side of the board. Then let's put the components from the gate driver loop onto the board. As you can see in the table, the components involved in the switching on and the switching off are different. In practical, a very convenient way to lay out is to put the gate driving capacitors and the resistors between the GaN devices and the driver chip, as you can see in the picture. For the bottom side cooling GaN devices, The layout rules are very similar. The only difference is for the bottom side cooling device, the GaN devices and the decoupling cap will be placed on the same side of the board. So here are the components for the power commutation loop. Then place the components for the gate driver loops. The layout rules are very similar. Then the step 3 is to connect the components with the magnetic flux cancellation techniques to minimize the string inductance. So what is the technique of magnetic flux cancellation? As you can see in the picture on the right, the current direction on the two adjacent layers are opposite to each other. So according to the Ampere right-hand rule, we can figure out the direction of the magnetic flux generated by the two conductors. And actually, in the highlighted region, the magnetic flux generated by the two current flows are canceling each other. On the other hand, the parasitic inductance is a function of the magnetic flux. So the magnetic cancellation technique can help reduce the parasitic inductance. In layout, if we can make the high frequency current direction opposite to each other on the two adjacent layers, the inductance will be minimized. Here are two examples of layouts of the top side cooling and the bottom side cooling devices. As you can see in the picture for the power commutation loop, and the flux cancellation techniques are applied to minimize the loop inductance. The last step is to verify the design by performing double pass tests. Double pass test is the first test we suggest doing after the board comes back from the assembly house. It is very necessary to verify the switching performance of the power stage before we power up the system and run it continuously. Because supposing if something goes wrong in the continuous operation, we have no idea whether the problem is caused by the layout, or is caused by control, or is caused by thermal. So it is very important to verify your power stage design with a double test. If we cannot solve the problem in the design review stage, let's catch the problem in the lab and solve it. Don't leave the problem to the production. A good GaN-based power stage design is able to handle hot switching at rated current. So we call this the GaN system standard. For a good power stage design, it should be able to handle the hot switching on the rated current. At the same time, the VDS overshoot should be minimized. Here is the waveform of 4 GaN devices in parallel and hot switched at rated current 240 amps. As you can see in the picture, the switching transition is very clean and reliable. The voltage overshoot on the rated current is only 52 volts. I hope after attending this webinar, you will feel the same way as I do. It is very easy to achieve such design in your system with GaN devices. If the power stage passes the double pass test, we can say the layout is good enough confidently, so we can focus on the rest of the system design without worrying about GaN. The last section is about the available GaN systems reference designs. Let's talk about the support and the resources you can get from us. If you click on the Design Center in our website, you can see there are many resources available. They are easy to find and easy to use. If you need more help, we have a global applications engineering team to support. We published many application notes talking about the layout, the gate driver design, the GaN devices parallel, the thermal design, the EMI filter design, and the dynamic anti-thumb. Please check them out on our website. The power stage design rules we discussed today are also included in our application notes. Please feel free to download them from our website. These are the evaluation boards we have for different power levels and different applications. All these information are available on our website. Also, you can purchase them from GaN Systems distributors. If you need a copy of the design files, please contact us. This is a summary for today's webinar. First, we hope you all agree that designing with GaN is not difficult. GaN has many similarities to silicon MOSFET. There will be some difference require attention to details, but there's no new concepts. We reviewed the most common first-time designer mistakes and discussed the effect of parasitic inductance. In the end, we summarized a few layout steps to maximize the GaN system's design performance. Okay, the first question reads, is GaN easy to be paralleled? And is there anything special for GaN in parallel? The answer is yes. GaN is easy to be paralleled. We have a GaN 2 in parallel and 4 in parallel reference design. The design rules are quite straightforward. The only special thing compared with a single GaN is in parallel cases, we have to make sure that the power commutation loop for each parallel device is minimized and symmetric. So if you refer to the application notes and G004, you can get more information. The second question is if the switching loss will be affected by the parasitic inductance. Yes, the answer is yes. So very obvious example is a common source inductance. It will just slow down the switching transition. And for some worst case, there could even be some fault triggering. So the switching loss will be very different. Another example is the power commutation loop inductance. It will just increase the switching, the voltage spike during the switching off transition. So this will also increase the switching off loss, but not a lot, just a little bit. On the other hand, if the parasitics is not very good, it's not very optimal, usually the designer has to slow down the switching speed. So in this scenario, the switching loss will be greatly affected by the increased RG. So the conclusion is yes. If we minimize the stray inductance, we also can minimize the system loss. Okay, I think time is up. Thank you all again for joining this webinar. If your question were not answered here, we will email you the response in the next few days. Thank you. Bye-bye.